Hello everyone, this is Dr. Webb. We've been using vector function parameterizations to build curves, and sometimes that parameterization is important. Sometimes we're talking about the motion of a particle or an object, and so that parameterization is telling us exactly where that object is at different times. But other times what we really care about is the curve itself. And the parameterization is really just there to get us to the curve. And so when we're thinking about just the curve, we kind of want to strip out any extraneous information coming from the parameterization that's not really inherent to the curve itself. So in this video, we're going to talk a bit about getting into some inherent important information about the curve. So if we have some vector function r of t, we know that its derivative, r prime, sort of called the velocity vector, then this is lying along the tangent to the curve. And so the tangent line to the curve, this does not matter on the parameterization. That's something inherent to the curve itself. But the magnitude of the velocity, which is the speed, right? This r prime of t that's the speed function. Well, the speed at which you move along the curve, that's really coming from the parameterization and not from the curve itself, right? And so we kind of want to strip out this speed and get just to this tangent line itself sometimes. And so this behooves us to define something based on r prime, which we're going to call the unit tangent vector, which is capital T of t. And what capital T of t is you just take the velocity vector. And so velocity vector, it's lying on the tangent to the curve, and its magnitude is the speed. So we want to strip out that magnitude. And so we're dividing by the speed. And so this is creating a unit vector. Right? And so this is giving a unit vector that's just lying on the line tangent to the curve at each value of t. Right? And so by dividing out the speed function, the magnitude of r prime, we're removing the speed by this particular parameterization. Right? And so if we're thinking about this as a picture, we have some curve, pick some point. Let's say the only thing really coming from the parameterization that's going to be preserved is which way you're moving along the curve. So if we're moving along this way, then r prime of t looks like that. Then the unit tangent is going to be just one long going in that direction. That's r prime, t, not t prime. We'll get to t prime later. Okay, and so if you look at the definition, we're able to find this unit tangent vector so long as we have r prime of t and it's not equal to 0. Right? And so when that happens, we're going to call a curve smooth. Right? And really, curve and the parameterization are smooth whenever the derivative is not equal to 0. Okay, so let's find this unit tangent vector. So we're starting off with this example in R2. So if you look at this, our x component is t, our y component is t cubed. And so what's the curve we're really drawing out? Well, if I cube x, I get y. So this is really drawing out a basic cubic. Right? And so to get the unit tangent vector, t of t is r prime of t divided by the speed. So we need to figure out the derivative first. And component by component, the derivative of t is 1. Derivative of t cubed is 3t squared. So there's our velocity vector. Now we need the speed, which is just taking the magnitude of this. And it is not a vector. And so x component squared is 1. Y component squared is going to give me 9t to the fourth. Right? And so t of t is going to be, take r prime, divide by its magnitude. So it's going to be 1 over square root 1 plus 9 t to the fourth. The y component is going to be 3t squared over 1 plus 9 t to the fourth. Okay, and so that is our unit tangent vector. Okay, so what's this going to look like on the graph? So let's clear out some of this space. We've got our unit tangent vector on the bottom. So let's copy it down up here. So we figured out that it's 1 over square root 1 plus 9t to the fourth, 3t squared over 1 plus 9t to the fourth. Now let's do some erasing. Oh, come on. Okay, we're decently good. Okay, so we said that this draws out a cubic. So let's draw out that cubic. Okay, and so when t is equal to 1, r of 1 is going to be 1, 1. And so that's going to be pointing at this point 1, 1 on here. So r prime at 1 would be 1, 3, because 3t squared, plugging in 1 for t gives me 1. And so that's going to be pointing up in this picture, something fairly big. Now when we plug this into t of 1, what do we get? Well, I'm going to get 1 over square root of 10, comma, 9 over square root of 10. And you can double check that that has length 1, and so that's going in the same direction, just going a little bit less. Okay, actually a fair amount less. Okay, so there's an example of unit tangent vector, and we can do this for any other spot on the curve. In fact, if we did this for at 2, so at 2, this is going to be pointing to 2, 8. The velocity there is going to be pretty big. So velocity, x component is going to be 1, but the y component is going to be 4 times 3 is 12. And so that's already a pretty big vector. So this is happening somewhere up here. And so that would be shooting way up big. But what about the unit tangent there? Well, it's going to be, let's see, 2 to the fourth is 2 to the fourth is 16 times 9. 90 plus 54 is 144, so this is over 145. Over 12 over 145. And so this, you can see, is going to be quite a bit more well behaved. So it's sitting right there like that. This unit tangent vector does not depend on the parameterization. So what I mean by that is that if we have two different parameterizations and they're moving in the same orientation, and so if this is our basic curve and they're both moving, orientation is talking about which way you move as t increases. So if they're both moving, in this case, from left to right, then at any point, even though their velocity vectors will be different, they'll be lying on the same tangent line. And if they're lying on the same tangent line, when you divide out by the magnitudes to get unit vectors, you're going to get the same unit tangent. Right? And so if you think unit tangent vector, it's a unit vector. So unit vector means it's lying somewhere on the unit circle. And so in this case, it would look something like this. And as t changes, we're just going to be getting different vectors, but all different unit tangents as t goes on. But they're all lying on this unit circle, okay? And so you can kind of think about the unit tangent, it's just kind of spinning around this circle. And so it's acting a lot like kind of a compass, right? So you can think about t of t is, it's like a compass for the curve telling us where we're going. Okay, and so if you think, the analogy I often use, I think I've used before, if you're thinking about r prime of t as you're driving, if you're driving in a car, r prime of t is your velocity, which is both your speedometer and a compass. The unit tangent vector is pulling the speedometer out of that, right? And so the unit tangent vector is just the compass. Now, if we start with the arc length parameterization of the curve, well, for the arc length parameterization, this is something we talked about in the last video. In the arc length parameterization, its speed is a constant 1. And so when we take the velocity vector, r prime of s, divided by its magnitude, well, its magnitude is already 1. And so that's going to give us a unit vector going along the tangent, and so that is the unit tangent vector. Right? So if you have an arc length parameterization, its derivative is always going to be the unit tangent vector, or a unit tangent vector. Okay, so next question, sort of revolves around, now that we have this unit tangent vector, well, kind of what happens when we take the derivative of it? And so we're going to do the same sort of trick as we did with t of t and get what we're going to call the unit normal vector, which is you take the derivative of the unit tangent vector and divide by its magnitude to give it to make it a unit vector, and we're going to call this the unit normal vector. Okay, and so what does this unit normal vector going to tell us? So what does n of t tell us? Why is this important to focus on at all? Okay, well, let's do a pretty straightforward example. So this is moving along a circle, and let's find both the unit tangent vector and the unit normal vector. So this r of t is drawing out a circle of radius 4, starting on the x-axis at t equals 0. If we do r prime of t, well, this is going to be derivative of cosine is sine, so I'm going to get minus 4 sine of t, for cosine of t. And because we've got sine and cosine in there, this is pretty quick to get the magnitude. It's going to be, we're going to have a sine squared plus a cosine squared in there. We can pull out the 4's, and we're going to get that this magnitude is always 4. And so this says that the unit tangent vector is going to be minus sine of t cosine t. Okay, so if we pick some point up here, this is at some t naught. Which way is it going to be going? Well, the tangent to a circle is always going perpendicular to it like that. In fact, it's always going perpendicular to the position vector, right? So that would be r of t naught. T of t naught is going to be looking like that. It's only 1/4 as long. You can double check here if you dot these two together that they're going to be perpendicular to each other. You're going to have minus 16 sine cosine plus 16 sine cosine, so they cancel off. What then is the unit normal vector going to look like? Well, to get the unit normal vector, this is the derivative of the unit tangent vector divided by its magnitude. Okay, so if we take the derivative of t of t, t prime of t is going to be derivative of minus sine is going to be minus cosine. Derivative of cosine is minus sine. Right. Since this is just cosine and sine, its magnitude is already 1. And so this is the unit normal vector. So our unit normal vector here, n of t, is minus cosine t minus sine t. Well, if you compare our unit normal, it looks decently like our original position function, except instead of multiplying by 4, instead of getting a radius 4, we've multiplied it by minus 1. Right? So what does that mean about the unit normal vector compared to the position vector? Well, it's actually going the opposite direction. And so it's pointing in towards the center of the curve. And since the tangent is moving perpendicular to the curve, and the unit normal is moving back in towards the center, that actually means that the unit tangent and the unit normal are perpendicular to each other. And again, we can check that by taking the dot product between these two. So if I do t dotted with n for any of these, I'm going to get minus sine times minus cosine. It's going to give me sine t cosine t. Cosine times minus sine is going to give me minus sine t cosine t. And so that's always equal to 0. So any value of t, the unit tangent and the unit normal are going to be perpendicular to each other. And that's actually not just special about this example, moving on a circle. This always has to happen. The unit normal vector is always going to be perpendicular to the unit tangent vector. Okay, and let me give you a couple different arguments to see what this is doing. So the first one, let's do this, make the first one sort of more geometric. Right? And so we talked about the unit normal vector, the unit tangent vector as being like a compass pointing on the unit circle. And so there's t of t. Well, it's always going to stay on this circle, right? So if time changes a little bit, It's just going to move to some other vector on the unit circle close to it, something like that. So let's call that t plus delta t, right? And so what's the change? The change is moving along that circle, right? And so if you're moving along the circle, you're going to be moving perpendicular to it, right? And so the unit normal vector is going to be going that way. It has to be. Okay, so that's sort of the geometric way of thinking about it. There's another way to see this. And so this comes from the fact that the unit tangent vector is always equal to 1. Its magnitude is always equal to 1. And so if we square it, it's still going to be equal to 1. Well, we can get the square of the magnitude of the unit tangent vector by dotting it to itself. Right? And now we're going to take the derivative of this. Okay? And so when I take the derivative on both sides, on the right-hand side, I'm taking the derivative of 1, so that's going to give me 0. On the left-hand side, I'm taking the derivative of a dot product. And so remember, when you're taking the derivative of the dot product, you got to use the product rule. And so this is going to be t prime of t dotted with t of t plus t of t dotted with t prime. And so really we have t prime of t dotted with t twice. So it's 2 t prime of t dotted with t of t is equal to 0. And then to make the left-hand side look like the unit normal vector, I just divide both sides by 2 times the magnitude of the unit tangent of the derivative of the unit tangent. But taking 0 and dividing by anything, that's not really going to change anything. And so this has to be t prime of t over its magnitude dotted with t of t has to equal 0. And this guy right here, that is the unit normal vector. Okay, so the unit normal vector always perpendicular to the unit tangent vector, right? And so, and you can see in this first picture right here, which way then is the unit normal vector going to go? Well, you're doing your unit tangent, and in this case, it looks like as you move, the tangent is turning to the left a little bit, and the unit normal then is pointing that way. And so the unit normal is always going to point in the direction that you're turning. Okay, so the unit normal vector, n of t, points in the direction the curve is turning. Right. And so if we have some general curve like this, let's say we're moving in that direction, the unit tangent is going to be right there. The unit normal is going to be pointing in, and as this goes along, you can see the unit tangent is going to be turning to the left there, and so the unit normal is going to be pointing in. And these two are going to be perpendicular to each other. Right? Whereas if we go up over here, unit tangent still pointing in that direction, but now we're turning the other way. N of t is going to be pointing in. If you notice on this curve, if you think about sort of inflection points, places where the concavity, so concavity is talking about which way you're turning, places where the concavity is changing, at that point there's not going to be any unit normal vector. At that point, really, the magnitude t prime, the magnitude of t prime is actually going to be 0, because t is sort of, I'm sort of thinking about points kind of like right there. It's not turning at all, and so there's going to be no unit tangent, no unit normal vector. Okay, but at places where it is turning, so it is turning here, it's turning in that direction. And so that's what the unit normal vector looks like geometrically. Okay, so in 2 space, the unit normal and the unit tangent vector are giving 2 different directions, and that's really all the different directions you can have in 2 space. But in 3 space, well, unit normal and unit tangents are going to be perpendicular on the same plane, and so then you can say, well, what then is a vector perpendicular to the plane? And we're going to call that b of t, which is just going to be the cross product of t and n of t. And this is called the binormal vector, right? And so this is following the right-hand rule. If you put your right hand along t, have n be, as you curve your fingers on your right hand, then b of t is going to be pointing up. So right-hand rule, here's t of t. Let's say n of t is perpendicular going off that way. Then b of t, the binormal vector, is going to be perpendicular to both of them, going up like that. Okay. And so what the binormal vector gives us, along with t and n of t, and so this is important sometimes in physics and mechanics, this is what's called sometimes the TNB framework, or TNB frame. And what this is this is a coordinate system so these are all unit vectors perpendicular to each other, kind of like I, J, and K, but it's the coordinate system, it's based on what the particle is experiencing as it moves along the curve. And so t is pointing in the direction that it's going, n is pointing in the direction that it's turning, and then b is giving the third component, right? And so there's some cases, sort of when you're thinking about, I think it's kind of called an inertial framework, where this can be important when you're thinking about the forces that are happening to an object as it moves along in space. This gives a easier sense of, often gives an easier way to do the calculations if you think about it in terms of these directions than in just sort of the standard XYZ. And that is all I have for you for this video. I will see you again later.